Hello everyone, welcome back. The topic for this video is thermodynamics. So we've already looked at thermodynamics a few times in General Chemistry 1 when we looked at the topic of calorimetry. You would have learned about the first law of thermodynamics, so energy cannot be created or destroyed. We also saw thermodynamics briefly in the topic on phase changes when we looked at enthalpy of vaporization or enthalpy of fusion. Okay, so you might want to go back and briefly review some of those topics on enthalpy and exothermic versus endothermic reactions. So we're going to start with the topic of spontaneity. So a spontaneous process is going to be one that occurs naturally under a given set of conditions without any addition of energy needed. So this could happen quickly or slowly. So it's important to know that we are talking about thermodynamics in this section, which is different than kinetics, right? So kinetics is going to be how fast or slow that a reaction occurs. Thermodynamics will simply tell you if a reaction will occur eventually, right? So it could happen quickly, like a combustion of gasoline. That's spontaneous, but rusting is also spontaneous, and you have radioactive decay. Another great example where some isotopes will decay very quickly within seconds, and some very slow over orders or magnitudes of billions of years. Okay, so spontaneous does not mean that a reaction is going to happen fast, and it does not mean that it's reversible. So reversible, we're going to talk about equilibrium in the next chapter. Okay, so we'll learn about whether or not reactions are reversible or irreversible. So spontaneous processes are going to be driven by the tendency of energy and matter to spread out or disperse. And so we're going to learn about entropy that describes this process. And it is also associated with a decrease in energy. So when we talk about a decrease in energy, we're talking about exothermic reactions. Remember that the enthalpy would be a negative delta H, or a negative change in enthalpy is an exothermic reaction. A positive delta H would be an endothermic reaction. Okay, so spontaneous processes are typically going to be associated with exothermic reactions and positive changes in entropy. Okay, so non-spontaneous processes, of course, are going to be the opposite. They're going to require a continuous input of energy, and they're not going to occur naturally. So these are typically the reverse of a spontaneous reaction, right? So we see down in the bottom corner here, we've got a valve separating two spaces, and when we change that valve or open the space between them and allow that gas to pass, of course that gas is going to move in the direction of filling both containers. And once both containers are evenly filled, you're not going to see it naturally tend back to all of the gas being located on one side without some sort of energy source to make that happen. Okay, some other examples of this would be freezing water. So we have to have a refrigerator in order to make that happen. And we're talking about freezing water at room temperature, right? So if you're below 0 degrees Celsius, then it will naturally freeze on its own. But if you were at room temperature, you're going to have to apply some amount of energy to cause freezing. And then electrolysis of water, of course, that's going to require electrical energy. So spontaneous processes are not random. They're going to reflect the natural tendency of matter to spread out. And this spreading out increases the number of possible arrangements of particles and energy, which we call microstates. And we'll talk more about that in just a moment. So a lot of this comes down to probability. So the more dispersed the energy in particles, the greater entropy that you're going to have. And again, a positive change in entropy is going to be related to a spontaneous process. So systems are going to tend from ordered to disordered states, right? And another great example of this would be our bedrooms or our houses. So our houses will tend to get messier if we don't put in the energy to clean them. Some other examples of this, we've got salt dissolves in water to have the ions separate. So, and again, any type of dissolving process or dissolution. And we see that here where we add a red dye. Of course, that red dye is going to spread out in the liquid until it becomes evenly dispersed. So that's going to be an increase in entropy there as well, and then ice melting into liquid water. Okay, so let's talk a little bit more about the definition of entropy and get to know this topic a little bit better. So we've already found out that entropy is a measure of disorder or randomness in a system. And so we're going to say that the change in entropy is equal to the heat of a reversible reaction. And we'll find out that it doesn't really matter for the purposes of our case whether that is a reversible or irreversible reaction. So we can assume that delta S, or the change in entropy, is going to be equal to heat divided by your temperature. And of course, remember that when we're dealing with temperatures, we are talking about temperatures in Kelvin. Right, so we've got to convert any of our degrees Celsius into Kelvin for equations. So the greater disorder in a system, the greater entropy that you're going to have. And entropy is also related to the number of microstates. Okay, so a microstate, and we've got 16 examples of those here. Okay, so we've got an example of a microstate where you basically have a number of boxes and a number of particles. So if you notice in this one microstate, we have two boxes. Okay, and so we're going to denote the number of boxes as an uppercase N. And the number of particles that we have, we're going to associate that with a lowercase n. Okay, and if we want to determine the total number of microstates, it's going to be the number of boxes raised to the power of the number of particles. Okay, so we have two boxes and a total of 4 particles to create a total of 16 different arrangements, or 16 microstates. Okay, and so if we look at the probability and we draw out all the 16 possibilities of microstates here, we find that the most probable orientation is if we have 2 particles in each box. Right, we get a total of 6 different possibilities there out of 16. And so based on the probability, you're going to have it more probable that you have an evenly dispersed system. And so that's why we see that we tend towards the greatest dispersal of particles. Okay, so this is just a very simplified definition of how this works. But if you look at probabilities, you'll find out that the larger probability is going to be whenever you have even dispersal of particles. And so we tend towards this dispersal of a system. So we're going to practice a question where we're looking at the definition of entropy. What is the entropy change when we have 2.5 moles of carbon dichloride difluoride vaporizes at 25 degrees Celsius? And they give us the delta H value. So remember that the equation for entropy is going to be delta S equals Q over T. Okay, and we learned in the section on phase changes that if we're looking for the heat due to vaporization, right, so Q of vaporization is going to be equal to the number of moles that we have times the delta H value of vaporization, right, because it's a conversion factor in kilojoules per mole. Okay, so if we want to find the value of Q, so Q of vaporization, we have 2.5 moles of our substance, so 2.50 moles, times our delta H value of 17.2 kilojoules per mole. Okay, so our moles cancel out. We've got 3 sig figs, and we're going to be left with kilojoules for our value of heat in the system. And so we get 43, but the calculator gives us 43. We want to keep those 3 sig figs, and so we're going to make it 43.0 kilojoules. Now, before we divide by the temperature, remember temperature always has to be in Kelvin. So we're going to take that temperature value of 25 degrees Celsius and add the 273.15. Okay, and remember that when we're adding values and focusing on significant figures, it's the shortest decimal place. So the 25.0 goes out to the tenths place of the value given, and so our sig figs will also go out to the tenths place. Okay, so again, it's not about the number of significant figures you have, it's about it going out to the tenths place. So we'll keep that 5 and subscript it to tell ourselves that it's not significant, but we're going to keep it to prevent round-off errors. So we have got our Q and our T. Now we can simply plug it in for our change in entropy. It's going to be the value of Q, 43.0 kilojoules, divided by that temperature in Kelvin, 298.15 Kelvin. Okay, and so 3 sig figs should be our least number of sig figs, and we get 0.144 kilojoules per Kelvin. Now, you'll find that most delta S values or change in entropy is going to be in joules per Kelvin. So you might want to switch this to joules per Kelvin, and of course that means that you're going to multiply by 1,000 joules per 1 kilojoule. Okay, and so we get 144 joules, right? Kilojoules cancel, joules per Kelvin. And just know that also most of your entropy values will be written in joules per mole Kelvin. So you might see this as 144 joules per Kelvin, or you might see them add the per 1 mole back into it. And so it's joules per mole times Kelvin. Okay, so you could see either of those. So entropy is a state function, which is different than a path function, right? So work we've seen is a path function. It depends on the path that you take. Enthalpy, delta H, was also a state function. So if you go back and refresh on Hess's law, when we were able to take several different reactions and add them together in order to get our final reaction, and we could simply add those delta H values together, that's because enthalpy was a state function. And so we can do the same things with entropy as well. And we've already seen the units are going to be joules per mole Kelvin. And delta S is positive if we have an increase in disorder and negative when we have a decrease in the disorder. So some common entropies or some common entropy increases would be if we increase the number of gas molecules. So remember that when we're talking about entropy, we are talking about the location and the energy of particles. Okay, so let's just write this over here to the side. Location and energy are the two main components when we're looking at microstates and entropy. So if you want to increase entropy, you're either going to have to increase the number of locations that those particles can have, the number of boxes, right, in that picture we saw for microstates. And the way we can do this is either converting a solid to a liquid to a gas, right? So gases will take up more space in a container. So location, we could change that based on the phase, or of course based on the container that it's in. If we're talking about a gas and we increase the container, like we saw with those two containers that were separated by that valve, and we open up that valve, then we have an increase in the location of our microstates as well, or an increase in the number of boxes. And then energy, of course, we're going to change that based on the temperature, right? So if we increase the temperature, of course, we're going to increase the energy of those gas molecules. And we can also increase the energy from the phase change as well, right? Because when you're in motion as a gas, there's more motion to that and more freedom than if you're a solid. So again, we can see entropy increase if we increase the number of gas molecules. So that's increasing the number of particles, which increases your number of microstates. Increase from a solid to a liquid to a gas, or if we have a solute dissolving in a solvent, again, you're going to increase the randomness there, and a temperature increase. Okay, so again, this just shows you that if we increase the temperature, of course, you're going to increase the amount of energy, right? So as we go from a lower temperature to a higher temperature, you can see that the average kinetic energy, if we look at the peak of each one of these, we're going to see an increase in the amount of energy there. Okay, and then of course we're going to increase in entropy either if we increase the temperature or if we have a phase change as well. If we go from a solid to a liquid, there's an increase in entropy, or from a liquid to a gas. Okay, so when we're talking about trying to determine which system will have more entropy, the first thing we want to look at is the phase. So gases almost always will have the highest entropy regardless of the type of substance that you're looking at. But if they have the same phase, then we're going to start looking at the types of molecules that we have. Okay, so when we look at molecular complexity, there's two ways that we can increase that. We can either increase the number of atoms. So we see we go from a 2 oxygen atom system to 3 oxygen atoms. Of course, that's going to increase the complexity. But if we change the types of atoms, so O3 versus SO2. Both of those have 3 atoms, but because now we have 2 different types of atoms, you're increasing the complexity there as well, and so you're going to increase the entropy. Now, if we have the same number of atoms, then we start looking at molar masses. So if we have the same phase and the same number of atoms, then as the molar mass increases, we're also going to have increase in entropy. And then, of course, dissolution. So if we look at something that is in its solid state versus an aqueous, when it dissolves and separates out into its ions, that's going to increase the entropy as well. Okay, so let's predict the change in entropy for a few of these everyday cases. So the first case, we have an ice cube that is warmed to near its melting point. Okay, so in this case, we're not changing the phase. We are staying an ice cube. We are not currently melting, but you are increasing the temperature. So if we increase the temperature, we're increasing the energy of those microstates. And so we're going to have a positive change in your entropy there. Second case, we've got exhaled breath. So our breath is a gas, and we're going to form fog. So that gas is condensing into a liquid. Okay, and so if we have less gas molecules, then we're going to have a decrease in the movement or a decrease in the freedom of rotation or freedom of movement of those molecules. So that's going to cause a decrease in your entropy. Okay, anytime you have less gas, you're going to have a decrease in entropy or a negative delta S value. Okay, we've got baking soda and vinegar react to produce carbon dioxide gas. So baking soda, we know that that's going to be a solid, and vinegar is a liquid. So we're taking a solid and a liquid and we are producing gas molecules. So of course, if we're increasing the number of gas molecules, okay, and same thing that happened here, we had a decrease in the number of gas molecules. Then that's going to cause an increase in gas molecules, will cause an increase in entropy, and so we'll get a positive delta S. And then the last one, a protein folds into a more compact 3D shape. Okay, so if we're folding and compacting this, we're going to decrease the amount of movement or motion or freedom of those atoms. And so anytime we're decreasing that movement, we're going to have a negative delta S, okay, or a decrease in the entropy of the system. So the last section for this topic, we're going to look at the second and third laws of thermodynamics. Okay, so the second law of thermodynamics tells us that for any spontaneous process, we are going to have an increase in entropy of the universe. So most of the time we've been focused on the change in entropy of the system. But remember, you've always got the system and the surroundings. And again, we talked about this in calorimetry, right? When you looked at a styrofoam cup that may have had a hot or cold liquid in it, that styrofoam cup and inside of it was your system, and then the air around it was your surroundings. Okay, so if we're looking at the total entropy increase, we've got to say of the universe, which includes both your system and your surroundings. So that total entropy change has to be positive. Okay, and so we look at this example of a hot object and a cold object. So we know that heat will always flow from the hot object to the cold object, right? This is a spontaneous process, but we're never going to see heat flow from the cold object to the hot object. That's a non-spontaneous process. Now, if the two objects were at the same temperature, then we would have the system at what we call equilibrium. Okay, so there would be no heat. There would be heat flowing back and forth evenly, basically. And so no overall heat flow in one direction. So when we look at this in terms of heat engines, the way heat engines work is that they have to have a low temperature sink where where your high temperature source is moving towards that low temperature sink. And so because of that, because you have to have this movement from the hot source to the cold source, you cannot have 100% of that heat being used towards work. And so the important thing here is that no heat engine can be 100% efficient. Okay, and that is based on the second law of thermodynamics. So the third law of thermodynamics tells us that the entropy of a perfect crystalline substance at absolute 0 Kelvin is defined to be 0. Okay, and so remember, for the purposes of this class, you cannot have negative Kelvin, right? 0 is as cold as you can get. So what that means is that the entropy values are always going to be positive. When you look at a table of standard molar entropies, you're going to see that all of them are positive. So unlike delta H, entropy values are absolute, they're not relative. And so again, when you look at those tables, you'll see the delta symbol in front of your H's and in front of your G's. We'll talk about free energy later, but you won't see a delta symbol in front of your entropy values. Okay, and just like enthalpy, your standard molar entropies are going to be 1 mole of a substance in its standard state. So 1 bar and 25 degrees Celsius. And so with this, we can do something very similar that we saw in Gen Chem 1 with our enthalpy values, where if we want to calculate the change in entropy of a reaction, we can look at the standard molar entropy values for our products and our reactants. And remember, it's going to be the total sum of our products multiplied by the moles or the coefficients in front of that substance, and then you're going to subtract out the sum of your reactants. Okay, and so if we get a delta S that's positive, a change in entropy for the reaction that's positive, that's considered a favorable reaction for spontaneity. It doesn't automatically mean that it's spontaneous, but it does mean that it's favorable towards being spontaneous. And a negative delta S value, of course, is going to be the opposite. You're increasing the order of the system, and so that's unfavorable. Okay, so let's look at some examples. We're going to calculate the change in reaction, or the change in entropy for the following reaction. We've got 2 molecules of hydrogen plus a molecule of oxygen yields 2 molecules of water. Okay, so when we are looking at the molar entropy states in a table, you may have to look this up in your appendix of your textbook. So that's where I got all of this information at. Now, when you're looking at the substances, make sure that you note the phases, right? So hydrogen gas, oxygen gas, and water in its liquid state. So we only have one option for the hydrogen gas, and we have 2 options for oxygen. Just make sure that you notice it is the diatomic oxygen, which most of the time it will be. So you do need the first oxygen listed, hydrogen gas, and then the important thing is the phase of that water, right? So water can exist as a solid, liquid, or a gas, and we want the one that is in its liquid state. Okay, so remember that the change in reaction is going to be the sum of the products minus the sum of reactants. So let's first look at those products, which is your water molecule. So delta S of the reaction will be equal to the number of moles. That's the coefficient in front. So we have 2 moles of water times the standard entropy for liquid water. Okay, so of course we're focused on that third column. We don't care about the first 2 yet. We'll do that in the next section. So standard molar entropy is 70.0. And that is joules per Kelvin times mole. Okay, and so the moles will cancel out, and so we're left with joules per Kelvin. Now that's the only that's the only product that you have, so now we can subtract out the reactants. And just make sure that you add up all the reactants before you subtract them. Okay, so we have 2 moles of hydrogen gas times the molar entropy for that hydrogen gas. So that's 130.7. Okay, and that's also going to be joules per Kelvin times mole. So the moles will cancel, so we'll always get joules per Kelvin back. And then we're going to add to that the oxygen gas, which is 205.2, and it's only 1 mole. Joules per Kelvin times mole. All right, so remember, because we have this combination of multiplication and addition and subtraction, we kind of want to take this one step at a time so that we don't get confused on significant figures. So in this first step, 2 times 70.0, that's going to give us 3 significant figures, and so we get back 140 with a decimal. Okay, so what's important is out to the ones place, and then past that we don't care. And then we're going to subtract from that 2 times 130.7. That's going to give us 4 significant figures because we have 4 sig figs in 130.7. So that's 261.4. Okay, so that goes out to the tenths place. And then add to that the 205.2. And we know that all of this is going to be in joules per Kelvin. Okay, so then again, make sure to add your 2 reactants together before you subtract them from that 140. And so you're going to get 140 with the decimal place minus 466.6. Okay, so ones place for the 140, tenths place for the 466.6, and so we're only going to go out to the ones place in our final answer. And so that should give us negative 327 joules per Kelvin for our final answer. And remember, it could be joules per Kelvin or it could be joules per mole Kelvin, just depending on what the source is asking for. Okay, but that's why it's so important that you do it step by step so that you know that you're ending in the ones place and not out to the tenths place. Oh, and let's check real quick. So does this make sense? So going back to whether or not the change in entropy should be positive or negative. So we have 3 moles of gas that we're starting out with in this reaction, right? We've got 2 from the hydrogen gas as well as 1 from that oxygen that's assumed to be a 1. So 3 moles of gas are producing 2 moles of a liquid. Okay, and so we should have a decrease in entropy, and so we should expect that that change in entropy for the reaction is negative, which we see. So it's always good to just double check and see, does it make sense? Okay, so we've got one last example for this video. We are given this time the reaction and the change in entropy for that reaction. We're also given the standard molar entropy for the product B, but we need to find the standard molar entropy for the reactant A. Okay, so of course we know that delta S of the reaction is going to be equal to the sum of the products. So we have 3 moles of B, which means it's going to be 3 times the standard molar entropy of B minus the 4 moles times the standard molar entropy of A. And so if we plug all of this in, we know the entropy of the reaction is negative 164.4 joules per Kelvin. And that is equal to the 3 moles times our molar entropy of B, which is 220.0. That's 4 significant figures. And of course the moles cancel, leaving us with that joules per Kelvin, and subtract out 4 times the molar entropy of A, which we don't know. Okay, so 3 times 220, of course, is going to give us 660.0 minus 4 times SA. Okay, and that's equal to that negative 164.4. So we're going to subtract the 660 from both sides. You could have easily added the 4 SA and then subtracted the 164. It's however you want to do this. But when we're subtracting the two values, they both go out to the tenths place. So we want to keep those out to the tenths place. So we get negative 824.4 equals negative 4 times the SA, the entropy of A that we don't know. Now they're both negative signs, so at this point we can make them both positive. And the last step would be to divide by 4 on both sides. Okay, so we've got 4 significant figures, which means we need to end with 4 significant figures, and so the molar entropy of A should be 206.1, and all of these molar entropy values, they are in joules per mole times Kelvin. Okay, so that should be the end of this topic.